Hey guys, welcome back. We're going to do number 116 from chapter 14 today out of the Trow second edition book. The rate constant for the first order, that's important, first order decomposition of N2O5. Right there, I'm going to write natural log concentration of N2O5 times T over the concentration of N2O5 times 0 equals negative KT. And T1/2 equals negative log of 2 over K. Rate constant K, lowercase. There we go. The rate constant is 7.48 times 10 negative 3 seconds negative 1 at a given temperature. Find the length of time required. That's our first order of business, is to find the length of time required for the total pressure in the system containing N2O5 at initial pressure of 0.1 atmosphere to rise to 0.145 atmosphere. So, what do we do? Well, write a balanced equation. It's always a good idea to write the balanced equation. What is our equation? N2O5 gas decomposing to NO2 gas and O2 gas. N2, looks like I need a 2 there. So that's 4. That's 5. I can do 1/2. There we go. Perfect. That works. We can do it that way. You can do 2, 4, or 1 as well. So we now have initial pressure of 0.100 atmospheres. There's 0 and 0 products. No atmospheres or products. And so we're going to introduce you now to this concept. It's a little early, but it's something called an ice table. Now, an ice table, when we get to in equilibrium chapter, has to do with initial change equilibrium. We're going to do that though, because we're going to do initial change in the end, because it's going to be the end of the reaction. We're assuming this is not at equilibrium. So there's going to be a change. Some of this is going to react. So some's going to react. Some's going to be made, and there's a 2 there. So 2x, and then half there, so plus 1/2 x. Right? For every 1 N2O5 that breaks down, I get 2 NO2s and 1/2 O2. We're talking about the mole ratio. So that means I have 0.100 minus x atmospheres, 2x atmospheres, and 1/2 x atmospheres. We know with Dalton's law of partial pressures that the total pressure is equal to the pressure of N2O5 plus the pressure of NO2 plus the pressure of O2. Okay, now we know the total pressure is 0.145 atmospheres. So I have the pressure total, which is 0.145 atmospheres, equals 0.100 minus x atmospheres plus 2x atmospheres plus 1/2 x atmospheres. So just doing some math. And it's all addition, right? So I have 0.100 minus negative x, that's 1. So that's 2x, 2.5x minus x would be 1.5x. Equals 0.145 atmospheres. And so we just move the 0.1 over. That would be plus 1.5 atmospheres. I'm sorry, it's plus. Put the 0.1 over, so 0.045 equals 1.5x. X looks like it's going to be 0.03 atmospheres. Wonderful. So now, the reason we had to do that is because for N2O5 here, we have 0.100 atmospheres minus x, or 0.100 atmospheres minus 0.030 atmospheres, which would be a 0.07. So that is the concentration of N2O5 at time t. And of course, 0.1 atmospheres is the concentration of N2O5 at time 0. So now we got our first order rate law. Natural log concentration of N2O5 at time t all over the concentration of N2O5 at time 0 equals negative KT. Let's plug in. Go down the line. Natural log of time t is 0.070 all over 0.100. Uh-oh. I'm doing atmospheres. Well, we know PV equals nRT. Is the temperature changing at a given temperature? No. The temperature is not changing. So we know the temperature is not changing. R doesn't change. Is the volume changing? It doesn't necessarily say the volume is or isn't changing. We're going to assume that this is constant, like we do with all our gas. So pressure is proportional to moles. And since if the volume is consistent, N over V would be moles over liters, it's molarity, so pressure is proportional to molarity. So whatever happens in the atmospheres is going to happen with the molarity. So we're good to go there. And negative K was 7.48 times 10 to the negative third. Seconds negative 1. And then we got T. So now we just solve for T. Do your natural log in the calculator, divide by K. And T equals, I got 47.68. Which equals 48 seconds. Perfect. So that's what I got for A, 48 seconds. B, find the length of time required for the total pressure of the system containing N2O5 if an initial pressure of 0.1 rises to 0.2. It's the same thing, except for we're going to have 0.2 here instead of 0.1. 0.45, 0.2. So I want you to try B. And you can, of course, send me an email question or whatnot if you don't get it. But you should be on the order of around 150 seconds, somewhere in that time frame. You're not going to get exactly 150 seconds. It's going to be a little bit less than 150 seconds, but about 150 seconds. C is a little different. C, we're trying to find the total pressure after 100 seconds. So now you actually have a different setup. So if we look at C, of course, C is set up the same way. We still have N2O5. We have decomposing. I'll put a plus sign. It's decomposing to NO2 and 1/2 O2. I'm starting with 0.100 atmospheres. None and none. We're going to add 2, so we're going to have 0.100 atmospheres minus x plus 2x and plus 1/2 x equals the total pressure. Now, we're looking for the total pressure. Great. If we go back to our E form, we'll use the E form. Sounds like we're doing electronic commerce or something. E form. I get N2O5 at time t, which we're looking for, equals N2O5 times 0 e to the negative kt. Well, we're really interested in N2O5. at time T. We know the original concentration is 0.100 atmosphere. And again, we can use the atmosphere because it's proportional to molarity. E to the negative K was, what was K? Negative 7.48 times 10 to the negative third. Seconds, negative 1. And T was, what, 200 seconds? So 100 seconds. Excuse me, 100 seconds. So if we do this math, I get the concentration of N2O5 at time T equaling 0.04733310. And obviously, that's too many figs. I can only do 0.473. So let's do that, 0.0473 atmospheres. So that's what I get. That's my concentration at time T. So what react? So this X here that we're talking about, this X is going to be the difference between the original concentration. So N2O5 at time 0 is 0.100 atm. And N2O5 at time T is 0.0473 atmospheres. So if we subtract those, I will get 4x 0.053 basically, because I don't have that data there, atmospheres. That's how much reacts. That's equals x. So now all we have to do is total pressure would be equal to the pressure of N2O5 plus the pressure of NO2 plus the pressure of O2. So my total pressure would equal, well, the pressure of N2O5 at this time would have to be 0.047 atmospheres. Qx here is NO2 plus 2 times 0.053 atmospheres. And O2 is 1 half x, right? 1 half x, 1 half x. 1 half of 0.053 atmospheres. That means my total pressure should be 0.179 atmospheres. You might have gotten, or 0.180 atmospheres. Either way works out good for me. So that's how you would do this problem 116. Hopefully that makes sense. It's a lot to unpack. It's very similar to some of the other ones, it's just in gases. So it's very similar to some of the other ones we did with the hydrogen peroxide or the sucrose. But it's a good problem. So hopefully that makes sense. Let me know if you have any questions. Take care, guys.